Hi guys, good morning. Uh, everyone doing well. I think we saw on Friday, correct? Okay, so we'll continue. Yeah. So let me share my screen. This is 12. Okay. So last class we just saw the introduction about electrochemistry, right? So I told you how a potential is developed, right? So when I have, yes, go on.
We didn't receive our exam paper yet, sir. The results we didn't receive.
Maybe you should ask Akila ma'am. That would be better because I have corrected the papers and I've given to her, like to the management. You can ask Raghav sir or Akila madam. Like they'll help you out with it. Okay. Right. Cool. So last class we saw how a potential is developed, right? So if I have an electronic and an electrolytic conductors in contact, right? If I have electronic and electrolytic conductors in contact, say this was the thing, right? Say now I had some piece of rod. Say now, depending on these two values, solution pressure and osmotic pressure, right? So here, from the electrolyte to the electrode. Oh, sorry, it's different. So here it is, right? If the ions move from the electrode to the electrolyte, that is called solution pressure. And here it is opposite. Like say it is going to be from the electrolyte to the electrode, right? Say if at all you are going to have a solution pressure dominating, right? If the solution pressure is greater than the osmotic pressure, you will see that the ions are going to move from the electrode, that is the electronic conductor, and to the electrolyte to conductor. So what happens? So if this gives me more amount of, say this is ZnSO4 solution, and this is your zinc rod, right? So now from this, Zn2 plus ions are going to go inside the solution. So what is going to happen? I am going to develop some negative charges on the surface, right? And surrounding this, there'll be so much amount of positive charges. And because of the separation of charges, I am going to have some potential development. Okay, now I can have the exact opposite. If I have osmotic pressure dominating than your solution pressure, that is from this, if I have ions moving to the electrode, then you will have the charge separation to be different. On the electrode surface, you will have positive charge, and in the electrolyte, you will have negative charge. Right? So again, since there is a charge separation there, you will see that there is going to be a potential development. Okay. Now, this actually, I forgot to tell you one point, people. This potential you see, right? This potential we call it as E. Okay, this potential we call it as E, right? This is actually connected, right? This is actually connected to one thermodynamic quantity. Okay, this is connected to one thermodynamic quantity. Okay, now that quantity is delta G. Right, we spoke about, maybe okay, we'll speak about it later, not now, maybe. Fine, no issues. So then we went on to see what are the different types of cells we have, right? Can someone tell me what are the two types of cells?
Galvanic cells, electrolytic cells.
Yes, right. So we have something called as galvanic cells and we have something called as electrolytic cells. Okay, so galvanic cells, what kind of chemical reactions we take?
Spontaneous chemical.
Spontaneous.
Yes, they take spontaneous chemical reactions. So if I consider the energy transformation, what energy is converted to what energy in galvanic cells?
Energy is converted to electrical energy.
Absolutely. Chemical energy is converted into electrical energy because all spontaneous chemical reactions are exothermic. That means
Exothermic.
they will release the energy, and that energy which is released is going to be converted into electricity. Right. So basically, whenever you have any power supply devices, as I told you, when you go to your physics labs, you give power supply to the resistors, or say your car batteries, your remote batteries. All these stuffs are giving you power supply. They're giving you electricity. Correct. So all these are going to come under galvanic cells. Okay. Now, an electrolytic cell is exactly opposite. I am going to take a non-spontaneous process, which is obviously going to be endothermic. Right. So for these reactions to happen, I have to supply energy. Right. Now that energy is supplied in terms of electricity, electrical energy. So here, what is the transformation? Electrical energy is converted into chemical energy. Basically, the electrical energy is used to make a chemical reaction happen. As simple as that. Okay. So now, as I told you, like we will be starting with galvanic cells first, and then we'll move on to electrolytic cells. Okay. Now, one of the very basic examples of galvanic cells is Daniel cell. Right. Now, Daniel cell is what you use in your physics labs generally. Okay. Daniel cell, maybe sometimes Lagrange cell is used, but 90% of times in all the schools, the laboratories and physics labs, they'll be using this Daniel cell only for giving power supply. Okay, fine. So I told, okay, before we move on to this, okay, now I told you that depending on which is higher, solution pressure is higher or osmotic pressure is higher, I will be able to develop some potential, right? But all I told you is you will not be able to measure this potential, right? You will not be able to measure the potential. What will you be able to measure is if I connect two such things, say this is a zinc model, and if I have say copper, whatever, in the same kind of stuff. Now say this is E1, whatever that is developed is E1. Now for copper, say the potential developed is E2. Now again, E1, E2 separately cannot be measured, right? But with the help of a voltmeter, if I connect it with the help of a voltmeter, I will be able to find this value. E2 minus E1 can be calculated. Okay, and I will tell you a method by which you will actually be able to calculate E1 as well as E2. We'll see about it later, right? But for now, this absolute potentials cannot be measured. Only the potential difference between these two can be measured. Okay, fine. Anyways, this is what I want to tell you, right? So now we'll see how a Daniel cell looks, right? What is the working, right? All these things we'll try to look into. Now we'll look into the construction. Okay, now see, Daniel cell, whatever it is, now for all galvanic cells, right? For all galvanic cell, the overall construction is going to be same, right? Overall construction is going to be same. Anyways, we'll look into it, right? So I am going to have two compartments. Okay. Right. Now this side, I'm going to have zinc sulfate, and into the zinc sulfate, I am going to have this is zinc rod, and I have another compartment which I have copper sulfate solution, and in this I'm going to have copper rod getting inserted. Okay, right. Now I told you galvanic cells are used for what? For producing electricity. Right. So I have to check whether any current or voltage is getting produced. Correct. So for that purpose, what I do is I put a bulb. This is a bulb. Okay, just to check whether any electricity is coming or not. Obviously, the electricity comes, the bulb will glow. If not, this thing will not glow. Okay. Now, other than that, I have one more thing. Right, I have a connection other than the wired connection. I have some connection like this between these two. This is what is called as your salt bridge. Okay, now we'll speak about it later. What exactly is the use of this? Why are we using this? How do you prepare a salt bridge? All these things we'll see later. Okay, but for now, we will try to understand whether the current is flowing or not. I'll tell you what is the use of salt bridge in a while. Okay, fine. Now, people. Now, please understand, I want you to remember one term, right? The term is LaO. Okay, LaO is left anode oxidation. You have to remember this code, LaO. Okay, left anode oxidation. Right now, what do you mean by this? Now, please understand, people. Any cell for that matter, right? Not only galvanic cells, any cell, galvanic cells or electrolytic cells will have two stuff. Like one is what is called as cathode, the other one is what is called as anode. Right? So we generally say that cathode is the one which is connected to the negative terminal of the battery, right? And anode is positive terminal of the battery. Like this is a general the conception. Remember like this, cation is positive, cathode is negative. Remember it like that. Okay, cations we know are positively charged, right? Cathode will be negative, and obviously anode will be positive. Okay, fine. So what I'm trying to tell you from this particular code LaO, left anode oxidation, is like you have to keep the anode in the left hand side. See, in this case, this whatever I have, this zinc rod is going to act as anode, and this copper rod is going to act as cathode. Okay, now remember this, always remember this. Okay, left side I'm going to have anode, and in anode I'm going to have oxidation happening. So obviously in the right hand side, right, in the right hand side I'm going to have cathode, and in cathode I'm going to have reduction happening. As I told you, we are going to connect chemical reactions with your electricity, right? And what type of chemical reactions we see? I told you that the chemical reactions we are going to see are nothing but oxidation and reduction processes. As simple as that. Okay, oxidation and reduction processes. And even last class, I told you that there is a difference between chemical reaction and an electrochemical reaction, right? So for a chemical reaction, we need the chemicals to be in contact, right? But for an electrochemical reaction, you see there is no contact here, correct? I mean, they are not in full contact, right? So you see this particular, chemical and this chemical are not in contact, right? They are connected via circuit, electrical circuit, correct? So whatever the reaction is going to happen here, that is what is called as your electrochemical reaction, right? Okay, fine. So as I told, left anode oxidation, cathode will be on the right hand side, and always in the cathode you will have reduction happening. Okay, always in the cathode you will have reduction happening. Okay, if you remember this LaO, that is going to come out naturally out, right? Left anode oxidation, if you remember, obviously in the cathode, I mean right hand side I will have cathode, and in the cathode I will have reduction happening. Okay, fine, cool, we understood this. Now what exactly is going to happen here? Okay, now look at this, people. I have zinc, I have copper. Okay, now from your previous knowledge, can you tell me which one is more reactive among zinc and copper?
Sir, I think it's zinc.
Okay, yes, zinc is more reactive. Okay, zinc is more reactive than copper. Now, when I talk about reactivity, people, when I say reactive, that too, when I talk about metals like zinc and copper or aluminum, sulfur, sodium, something like that, when I say reactivity or when I say it's reactivity, I am actually talking about electropositivity, right? I'm talking about electropositivity. What is electropositivity, people? What do you mean by electropositive?
Tendency to lose electron.
Yes, absolutely. Right. So electropositivity means it is the ability of the element to lose electron, or in other words, it is the ability of the element to form a positive charge. As simple as that. Electropositivity. Electronegativity means ability to accept electron, obviously to form a negative charge, that is anion. Okay, so electropositivity means it has whichever has electropositivity in general means ability to lose electron, and obviously if you lose electron you will form a cation. Okay, so when we said that zinc is more reactive than copper, right? When we said that zinc is more reactive than copper, that means zinc has more tendency to form a positive charge than when compared to copper. Okay, zinc has more tendency to form a positive charge than compared to copper. Okay, now please understand, people. That is why we mentioned it here. Oxidation. Now we know oxidation is what? Oxidation is loss of electron. Correct. Oxidation is loss of electron. Reduction is gain of electron. Okay, so if you have two substances like this, okay, when you have two elements, right, which will you choose as anode, which will you choose as cathode, is going to depend on the electropositivity. Okay, it is going to depend on the electropositivity. So this is the thumb rule you can follow. The thumb rule is more electropositive. Okay, so more electropositive metal should always be in the anode, right? So when you have confusion between two, when I give you two elements, okay, and you have a confusion between which should I put as cathode and which should I put as anode, right? All you have to understand is the more reactive, or say the more electropositive metal will always act as anode. Why? Because when I say electropositive, that means they're going to lose electron, and that's exactly what we have in the case of oxidation, right? In the anode, I need to have oxidation happening, right? So whichever has more tendency to undergo oxidation, or in other words, whichever has more tendency to lose electron, that should be the anode. And that is exactly what is mentioned here, right? So I can say more electropositive, or I can even write more tendency to undergo oxidation. Obviously, more electropositive means more ability to lose electron, and obviously more ability to lose electron means more tendency to undergo oxidation. It's all connected. Electropositivity and oxidation reduction, everything is connected. Okay, so if I give you a choice, if I give you two elements, now you will be able to choose which is going to act as anode and which is going to act as cathode, depending on the electropositivity. Okay, I hope this point is very clear. Okay, and that is the reason why we know zinc is more reactive, that is more electropositive, or more tendency to undergo oxidation. That is why we have put it as anode. And copper being less electropositive, less reactive, less tendency to undergo reduction, or in other words, more tendency to undergo reduction, something like that. Okay, so Nick, if you can even include this point, the less electropositive metal should be in the cathode, or the element should be easily or more tendency to undergo reduction, right? So among, if I have two elements, right, whichever is capable of undergoing reduction easily, okay, that should be in the cathode. Okay, now before we move on to see the working of how this is exactly going to work, let me give you this example. Maybe if I give you Ag, okay, and another element I give you is chlorine, okay, Cl2. Okay, now think and tell me properly which is going to act as anode, which is going to act as cathode.
Ag is anode and Cl2 is anode.
Absolutely correct, right? So Ag is a metal, obviously it will undergo oxidation, so this will be the anode, and obviously chlorine is electronegative. It's not even electropositive. We say less electropositive, or you can even write like this: less electropositive or more electronegative element should be in the cathode. So obviously chlorine is more electronegative, so that will be in the cathode.
So I have a
No
doubt.
issues? Yeah, please tell me.
So can this take place between two electronegative elements also? Sir?
Yes, absolutely, absolutely. Why not? Say for example, if I have chlorine, okay, I'll write, okay, chlorine and bromine. Say I take chlorine and bromine, right? Now, obviously, now which is more electronegative?
Yeah.
What? Which one is more electronegative?
Chlorine.
chlorine is more electronegative. So obviously chlorine again will be the cathode and bromine will act as anode. Right? So it's all correlated. Right? So more electronegative element, cathode, more electropositive element, anode. As simple as that. Yes, did I answer your question, Kanna?
Yes,
At the same way, can two electropositive elements be used to produce electricity?
Absolutely right. That's what we're doing here. More two electropositive elements, zinc and copper. So more electropositive element anode, less electropositive element cathode. Yes, understood?
Yes, sir.
Okay, absolutely. Good. So now we are now, and we understood what exactly can be chosen as anode, what exactly can be chosen as cathode, and what is going to happen in anode, that is oxidation, and what is going to happen in cathode, that is reduction. All these things must be in your fingertips. Okay, right? Fine, absolutely. Now we'll see how it works, right? How exactly is the working of this particular Daniel cell. Okay, right. Now I told you that anode oxidation is going to happen, right? How oxidation will happen? Now obviously means what? This zinc rod I have here is going to undergo oxidation. That means this zinc rod, which has zinc in the metallic form, Zn is only there. Now from this, I am going to have more amount of zinc 2 plus getting formed. That's what we saw when we looked into this potential, how is it getting developed. Right? If you look at the potential, how is it getting developed? This is exactly because the ions move from the electrode to the electrolyte, there'll be some potential developed, and that will naturally happen. Correct? Right? So now this naturally will happen. Right? So what will happen? So I have, maybe I have to take it little down and I'll again show you. So guys, this anode and cathode, okay, this anode and cathode can also be called as half cells, right? So whole cell contains both cathode and anode. So if I talk about only one of them, that is only anode I speak, or only cathode I speak, now that anode or cathode separately alone, without the other one, are what are called as half cells. Okay, so now they will tell like something like this: half cell reaction, right? So I will tell like this: anode half cell reaction means what? Basically, in the anode, what reaction is going to happen? I know it is oxidation, but what exactly is the oxidation? Now you have to understand, guys. Now that's how I told you that zinc in the metallic form will go into the solution as zinc 2 plus. Correct. Now, how can I form zinc 2 plus from zinc? How is it possible? Tell me what I have to do. Again, I repeat the question. How can I form Zn2 plus from zinc? What should happen?
Electron must be.
Absolutely. It has to lose electron. Correct. So zinc will lose. Oh, sorry. Zinc will. Right. So zinc will form Zn2 plus. How? By losing 2 electrons. Right. Okay. And obviously, this is oxidation only. Loss of electron is oxidation, and that's exactly what is happening here in the anode half cell. Right. This is the anode half cell reaction. Okay. Now, when I go to cathode, right? When I go to cathode, now obviously reduction has to happen. So what will happen here? Now, if I have this thing, right? So Cu2 plus ions are there already in the form of copper sulfate, Cu2 plus ions, SO4 2 minus ions are present. So this copper 2 plus are going to go into the copper as copper. I can say copper 2 plus will go as copper metal. Okay. For that, obviously, I have to accept electron. Right. So if I write the cathode half cell reaction, that would be copper 2 plus, obviously, I have to write copper 2 plus will accept this 2 electrons will to form copper. Okay, so in anode, I have oxidation happening, that is zinc losing 2 electrons to form zinc 2 plus, and in cathode reduction is happening where copper 2 plus accepts 2 electrons to form copper. Okay, now if I have to, there is obviously, this is one half reaction, this is another half reaction. So I can write the overall reaction to be what? Overall reaction, you have to just add these two reactions, right? One anode half cell reaction and cathode half cell reaction. You just have to add, but there is something else you have to do that we'll see later. What exactly are we going to do? Okay. Now, if you just add these two, can I tell that 2 electron and 2 electron gets cancelled? Right. So the overall reaction I can write like zinc plus copper 2 plus will form zinc 2 plus copper. Right. Okay. Now this is very similar to the overall. This is very similar to the normal chemical equation we see. I can write the same thing chemically. If a normal chemical reaction, say if I have zinc reacting with copper sulfate, basically that's what is copper 2 plus. Okay, zinc reacting with copper sulfate to form zinc sulfate plus copper. These two are exactly same, right? So you can make this reaction happen if I have a solution of copper sulfate and you put zinc into it, actual contact. But you see, this reaction is also made to happen, but not in contact, but just by connecting with the help of a circuit like this. Okay.
So
Now you can
you
ask.
say the first reaction is electrochemical and the second one is the normal chemical reaction.
Yeah, this one. This is my electrochemical reaction. This is a normal chemical reaction. Yes, absolutely.
Okay, so
Okay, right. Now, you can ask me, sir, where are these 2 electrons coming from? Right. Copper accepting 2 electrons to form copper. Where are these 2 electrons coming from? Can you answer this question and think and answer me this question? Where are these 2 electrons coming
Through
from?
the wires.
Absolutely. Okay. From wires. What is the source of it?
The anode
NSO4.
solution, that is ZnSO4.
Absolutely right. You see that the zinc is losing 2 electrons. Correct. Now those 2 electrons are going to come from here. They are going to travel, and they are going to come here. This is the direction of electron flow. That is why we basically have a bulb. I mean, that is why we actually have a wire. Right. So the zinc has lost 2 electrons. These 2 electrons will move through the circuit into the solution. So now this copper 2 plus will accept the 2 electrons to form copper. Okay. So I'm telling you that this is the direction of electron flow. Right. If this is the direction of electron flow, what should be the direction of current flow?
opposite direction.
Opposite. Yeah, obviously. Correct. The direction of current and the direction of electron are in the opposite direction. So I will tell you that this is the direction of current. Now, what do you understand? Now, because of oxidation reduction, because of loss of electron and acceptance of electron, the electron is moving from one half cell to the other half cell. So obviously there is movement of electron happening. Right? Because of the movement of electron happening, some current is also getting produced. So now the bulb will glow. Okay. Now the bulb will glow because of the movement of electron. I want everybody to give me a yes if they understood this in the chat box, or you can open unmute yourself and speak. Yeah, please go on.
This electron transfer from zinc sulfate to the copper sulfate solution takes place in the salt bridge, sir. Or through the wire.
No. Salt bridge has different criteria. I'll tell you what is the role of salt bridge here. Okay, the electrons are transferring to the wire which you connect. Right, you see the wire which is connected to the bulb. Right, through the wire it gets transferred, and that is why we say that through this wire only current will flow. No, current and electron are not different thing. This is going to be the opposite direction. So through the wire I have the current flow. I mean the electron flow. Obviously to the same wire I'll have current flow, but in the opposite direction. Salt bridge has different thing. I'll tell you what is the use of salt bridge. Right. Okay. Right. Fine. So guys, I hope everybody understood. I just want an S. I got so many chats. Okay. Good. Okay. Yes. Okay. Good. Fine. I hope everybody is following. Absolutely. So this is what is exactly my Daniel cells is working. Okay. Now, I have like everybody should understand what is a anode half cell reaction, what is cathode half cell reaction, and how do you write the overall reaction. Okay, and obviously you have to understand from where to where the electron flows, and obviously the opposite direction will be the direction of current flow, and the bulb will glow. Absolutely true. Okay, now the only thing which is left is the salt bridge thing, isn't it? Right? What is the use of the salt bridge? Okay, now for that, guys, I have to redraw the diagram again for you to understand. Okay. right? So this is your zinc sulfate. This is your copper sulfate. Right now, I'm not going to put the this thing circuit on all. I'll just put the salt bridge. Okay. Okay. Right now, guys, if you look at this, right, what is happening? I'll just put the zinc rod alone and copper rod also. Okay. Now you see that the electrons are getting lost by zinc. Right. The electrons are getting lost by zinc. So what is going to happen? This solution becomes more and more and more positive, right? The solution becomes more and more and more positive, right? And obviously the rod will become more and more and more negative. Am I right? Zinc is losing electron. I'm sorry, guys. This is exactly opposite. One second. Okay, right. So right, so I draw it. Okay, now what is happening? Zinc rod is losing electron, right? So zinc rod is losing up a negative charge, so zinc rod will be positive, right? But the surrounding solution will be negative, right? Surrounding solution would be negative, correct? Right. Now in this case, copper's basically copper 2 plus is accepting electron, right? This is accepting electron, correct? So this with accept electron, I am going to have, or say copper going to copper 2 plus. Am I doing it correctly? 1 second. So more amount of zinc is losing electrons. So okay, I would say there's more amount of Zn2 plus ions are more formed. So this would be positive. Okay. Fine. Okay. Now I'll just give you a clear-cut idea, people. Right. So inside the solution, I'll just zoom it here. Inside the solution, you have, say, zinc is forming Zn2 plus. We'll keep it like this, right? Zinc is forming the more amount of Zn2 plus. So more and more amount of Zn2 plus will be formed. Correct? More and more amount of Zn2 plus will be formed. So the solution will be positively charged. Okay. Right. Now here, the amount, there is some amount of copper 2 plus, and that copper 2 plus is going as copper. Basically, the amount of copper 2 plus is keep on reducing. Correct? The amount of copper 2 plus is keeping on reducing. So here inside, I will have so much of negative charges. I hope this point is very clear. Okay, again I repeat, zinc rod is forming Zn2 plus ions. Right? So more and more amount of Zn2 plus ions are produced inside the solution. Right? So obviously the solution becomes more and more positive. Right? Here what is happening? The copper 2 plus ions are going as copper. Right? So I will have lesser amount of, like say the positive charge keeps on decreasing, or I can tell that the solution in this case will be negatively charged. Okay. Now what is going to happen? Right? Now, after, yes, go for it.
Sir, but the electrolyte solution is accepting electrons, no, sir. So
Electrolyte solution is which electrolytic solution in this case?
zinc, sir. Zinc,
Here.
sir, so it is accepting electrons, right, sir, from the zinc
Absolutely.
one. So
Correct.
it become positive, sir. So
No, if it is going to accept electron, electron is negatively charged, so it will become more and more negative only. Yes.
Yeah, but you said zinc electrolyte will be positive, right, sir?
Zinc electrolyte is positive, obviously, because it is losing electron, and here it is gaining electron, so it is negative. Correct only, right? Oh, you're talking about electrode. Oh, no. Electrode is just for the.
Sir, no, sir. Zinc rod will be positive and zinc electrolyte will be the opposite, sir.
No, how you have to see this is don't talk in terms of electron. You just talk in terms of what is getting formed. More amount of Zn2 plus is going into the solution, so solution will be positive. Now here, the copper 2 plus is going from the solution to the electrode, so this is losing positive charge, so it will become negative. That's all you have to understand. The electron part comes here. That is just for the transfer here between the two electrodes. Okay, you don't have to worry about it. Okay, fine. So now why did I say all this is because we are looking into salt bridge. What is the use of salt bridge here? Now guys, now you see the solution is becoming more and more and more positive. Okay, solution is becoming more and more and more positive. So you understand, say from a neutral species, I have a neutral species and I have a positive species. Now from where it is easy to remove electron? Think and tell me. I have a neutral species, I have a negative species, from where it is easy to remove electron?
A negative species, sir.
No, I mean basically this is neutral species and positive species, from where it is easy to remove electron.
Neutral species, sir.
Yes, absolutely right, because positive species already have deficit of electron. Right, positive species has already deficit of electron, so removing more electron from positive species is very difficult. Okay, removing more electron from positive species will be more difficult than from a neutral species, because neutral species is neutral, I can remove electron. Right. Now, same way, if I have a negative species and a positive species, where it is more easy to add electron, where it is more easy to add electron, positive, negative. Positive, absolutely. Opposite charges attract, absolutely true. So I have more and more positive charges there, more and more is easy to add the electron. Okay, this point you understand. Now you look at the solution here. Now the solution here in the case of zinc sulfate is becoming more and more positive. And what is happening in this half cell? In this half cell, I have to remove electron. Correct? Right. Same way here, you see the solution is becoming more and more negative, and this has to accept electron. And both these processes are going to become difficult. Why is it difficult? From a positive species, it is more and more difficult to remove electron, right? And this solution is becoming negative, and to a negative thing, it is more and more difficult to add electron. Obviously, this is addition of electron, adding electron, right? This is removal of electron, right? So removal of electrons from positive species is becoming more difficult, and addition of electron to the negative species again more difficult, right? So what do you mean by this is because so if you don't put the salt bridge, right, if you don't put the salt bridge, there will be so much amount of positive charges form. So after a point of time, you will see that there will be no current flow, right? There will be no current flow because the electron removal and the electron accepting process is becoming more and more difficult because of the development of positive charge on the anode and the negative charge on the cathode side, right? So now the salt bridge is going to help us come through this problem, right? So now first we'll understand how to make a salt bridge. Okay, now what do you do to make a salt bridge is you take a filter paper, right? Now you take the filter paper, dip it in some electrolytic solution, say KCl solution, right? And then you roll it. Roll it means like this. Say if you can look at my video, say now filter paper will be like this, right? So you do it like this. It will become like a strip, right? And you take that strip and you insert it in both sides. Hope you understand. You take a filter paper, dip it in KCl solution, and then you roll it like this. So it becomes like a strip, and you keep the what is that? And you keep the both the ends in the both anode and cathode. That's it. That's very simple. That is exactly what is a salt bridge. Okay. So what you understand is there is going to be some K plus ions, some Cl minus ions. All these things are going to be there in the filter paper. That is the salt bridge. Okay. So what is going to happen now? In this case, I have more and more amount of positive charge in the zinc side. Right. So what is going to happen is this chloride ions are going to come here and neutralize them. Right. The chloride ions are going to come inside and neutralize them. Now, if they neutralize, what will happen? Now the electron removal process becomes more easy. Correct. Because only if there's a high amount of positive charge, removing electron is going to become more difficult. Right. But if this chloride ion is going to come here and neutralize the positive charge, now the electron removal process becomes more and more easy, right? And same way, this K plus ion are going to go into this side, right? There is excess amount of negative charge, and that is why addition of electron becomes more difficult. Now this K plus is going to move here, and it is going to neutralize this negative charge. Okay, thereby the electron addition process becomes more and more easier. Okay, so if someone asks you what is the role of the salt bridge, right? The role of the salt bridge is to maintain electroneutrality. Right, obviously that's exactly what they're doing, right? The positive charge is getting neutralized by Cl minus, and the negative charge this side is getting neutralized by K plus. Right, so if you maintain charge neutrality on both the sides, the process keeps on continuing, or else after a point of time the electron removal process becomes difficult, electron addition process becomes difficult, and eventually the process will stop and you cannot draw any more current from the circuit. Okay, so the role of salt bridge is this: maintaining electron neutrality, right? Maintaining electron neutrality in both cathode side and the anode side. Okay, so I hope everybody understood how do you make a salt bridge, and what is the use of salt bridge, and how is it maintaining electron neutrality, right? Maintaining electron neutrality, everybody will tell you. But how is it maintaining electron neutrality? This is exactly how it is maintaining electron neutrality. Okay, I hope everybody understood. Please don't mind. Again, I want a yes from everybody if they understood. Please go for it. If they understood the role of salt.
Cl minus will go to the anode side and K plus will go to the cathode side, right?
Absolutely, absolutely, yes.
Sir, one doubt, sir.
Yeah.
So can we use any other salt solution other than KCl?
Yeah, anything which can give me positive ions and negative ions, good amount. KCl is a very good electrolyte, right? It should anything which can give me high amount of positive ions and negative ions, anything, K2SO4, Na2SO4, anything is fine. I just gave you an example.
Okay.
Right? Okay. So yes. Can I get a yes from everybody?
One doubt, sir.
Fine, guys. Yeah, please go on.
Sir, you said the K plus ion will test this thing, the copper electrolyte. No, sir. The KCl ion will utilize the copper.
Okay, excess negative charge. Yes, please tell
Sir,
me. Yes.
you said if there are positive ions, we can add electrons more easier. Like the addition of electrons will be easier, no, sir. So if it,
Correctly.
but now after the reaction, where is the positive ion, sir, in the CuSO4 electrolyte?
There is no need of positive, right? Like, see, the thing is, what I'm trying to tell you is, I am not, see, there is already negative charge. Okay, now there is no possibility that you can have positive charge coming here. Even you add the salt bridge or you don't add the salt bridge, there is no possibility that I can have negative charges here. I mean, positive charges here. All I can do is convert this negative into neutral. And by that, I am saying that the electron addition process becomes easier. If it is positive charge, yes, it will become more easier. But there is no way that you will be able to form positive charge. All this K plus does is just to neutralize the excess negative charge is getting formed. That's the role. All you can do is make it neutral.
Okay, sir.
By that, making it more easier. Okay?
Sir?
Right. Yeah, please go on.
The addition of species in neutral is more easy than positive, sir.
Addition of electron in okay, can you come with the question again?
No, sir. Addition of electron is easy in positive or neutral species, sir.
Obviously positive, right? If I have a positive species, that will naturally attract electrons. But the problem we have here is you will not be able to convert this, this negative charge I have here, you will not be able to convert it to positive. All you can do is convert it to neutral. Thereby, obviously, when I compare a negative species and a neutral species, obviously adding more electrons in neutral species is more easier. And when I compare neutral species and positive species, obviously positive species is easier, but we don't have that liberty. We cannot convert this negative into positive. All we can convert it into negative into neutral. That's all we can do. Yes, understood?
Yes, sir.
Okay, right. So I hope everybody understood. Now I can get a yes. If there are no questions, please go for it, guys. Okay, now I got some yes. Okay. Cool. I hope everybody is following, everybody is understanding. There are no doubts. Okay, absolutely good. All are good questions. Nice going. Okay, so we understood what is the role of salt bridge here and how do you make a salt bridge. All this stuff, everything is okay for us. Right. Now, fine. We understood the working of what is the time? Okay, we started the class by 9:45. Okay, fine. Right. So we now understood the entire working of this salt bridge. I mean, entire working of this Daniel cell. What is the role of salt bridge? How the electron is transferred from this side to this side? What is the anode reaction? What is the cathode reaction? What is the overall reaction? All these things we understood, and we understood that the bulb is going to now glow. Okay, fine. Now, if you want to measure what is the potential developed, right? I told you that this is going to have, say, this side I'm going to have one potential, this side I'm going to have another potential. So if you, I told you that the potentials, that is absolute potentials, cannot be measured, right? But what you can measure is the potential difference, right? So how do we measure the potential difference? Is very simple, guys. Again, I'm going to make the diagram, right? I'm going to make the diagram. Now, the only difference I'm going to do is, instead of a bulb, I am going to connect a voltmeter. Okay, I'm going to connect the, obviously, salt bridge is there. Okay, fine. Again, this is zinc sulfate, this is copper sulfate, everything is okay, same, everything is same. Okay, so now I will be able to measure this potential difference, and this value will be known to you. What is the potential difference? Okay, fine. Now, this we understood. Now the question is, can I, right? And first thing, okay, before that, this value, what we have here, can also be, will be actually what? Will be the difference in potential between these two. Correct. So always remember, people, the potential of a cell. When I write E cell is the potential, overall potential of the cell, or I can write this is the EMF of the cell. Right. So the overall EMF of the cell will be equal to E naught cathode minus E naught anode. Okay. Now when I can even put E naught cell here. Okay. So E naught cell, it's like what? The overall potential difference is equal to one potential minus the other potential. Right. So always remember, when you are going to calculate the potential difference, it is always the cathode's potential and the anode's potential. Difference between the cathode potential and anode potential. You should not write E naught anode minus E naught cathode, right? You should always write cathode minus anode. This is a very standard formula which you have to remember. And this E naught cell is what will be given by this particular voltmeter. Okay, right. Now, there is a reason why I put a naught in all of these, right? When I put E naught, it talks about standard EMF. Okay, just like you have standard enthalpies, standard entropies, you just put a naught. Standard gives to energy. In your 11th class, you would have studied, right? So like that, when I put a naught here, that means it represents a standard EMF. Obviously, I need to have some conditions, right? What are all the conditions? Standard conditions. If you look into the standard conditions are, it should be at 25 degrees Celsius, 1 atmospheric pressure, and the concentrations of all the electrolytes using zinc sulfate, use copper sulfate, or use any electrolyte, the concentration should be 1 molar, 1 m. The molarity should be 1. Okay, so if in these conditions you measure the potential difference, that is what is called as your standard EMF. Okay, in these conditions, if you measure the potential difference, that is what is called as standard EMF. Okay, what are the conditions? 25 degrees of room temperature, 1 atmospheric pressure, and all the concentrations of all the electrolytes should be 1 m. So basically, zinc sulfate should be 1 m, and copper sulfate should also be 1. Okay, right. Now, there is one more point I want to tell you, right, guys? Now, when I say potential in electrochemistry, I can have two types of potential. Okay, one is what is called as oxidation potential. The other one is what is called as reduction potential. Okay, oxidation potential and reduction potential, because we understand that two processes are happening here. That is, one is oxidation, the other one is reduction. So I will we have two types of potential. Okay, say this zinc giving Zn2 plus 2 electrons. This is an oxidation process, correct? So we generally talk about oxidation potential. Say now if reduction happens, we talk about reduction potential. But all these are going to be very confusing. Okay, all these are going to be very confusing if I'm going to use both oxidation as well as reduction potential. So from now on, right, when I say potential, right, it always by default it means reduction potential, right? It always means reduction potential. So whether I have an oxidation reaction or I have a reduction reaction, we always speak only and only about reduction potential. Please remember this. Okay, right. Now, what is the basic difference between these two? Now, the oxidation potential and the reduction potential magnitude is going to be same, right? Say oxidation potential is 5 volt, reduction potential will be minus 5 volt. It's just like that. Only the difference will be in their signs. Okay, same magnitude, but different signs is what we understand. Okay, so to avoid all these sign convention, all these sign problems, now from now on, when I say that I'm going to have potential, some potential, I always mean only reduction potential. Okay, right, fine. Now, basically this, look at here, I am telling you that I have E0 cathode. That means I have to take when I say again potential, that means I'm talking about the reduction potential. I have to take the reduction potential of cathode, that in this case is copper. And you see I'm taking the potential of anode, and the anode in this case is zinc, right? Again, I'm going to take the reduction potential of the zinc. That's all I have to know, right? So if I don't have the voltmeter, right? If I don't have the voltmeter, right? This value cannot be found out, right? So even if I have the voltmeter, I told you this individual values, that is E0 cathode and E0 anode, cannot be measured as such, right? So what are we going to do about it, right? How will we be able to measure the individual reduction potentials of all the elements? Okay, now before we move on to see how are we going to measure it, now I want to tell certain points to you, right? The points you have to understand is, now see, this is an oxidation reaction, right? And this reaction will happen spontaneously. Please remember this. Okay, this is an oxidation reaction and this is a spontaneous reaction. Okay, so when I speak about reduction potential for an spontaneous oxidation reaction, again I repeat, if I speak about reduction potential for a spontaneous oxidation reaction, this E0 value will always be a negative value. Please remember this. Okay, right? Now, whenever I have oxidation happening, right, and I speak about reduction potential, that potential will always be a negative value. Okay, but if I have reduction happening and you speak about reduction potential, that will be a positive value. Okay, now this will make more sense if we move on to see how are we going to measure it and what are all other things we can do. Okay, so for now, remember that there is oxidation potential, reduction potential, but we are not going to use oxidation potential at all. When I say potential, we always use only reduction potential. Okay, now we are going to see how are we going to find this individual elements is individual elements is reduction potential. How are we going to find it is what we are going to see. Okay, right, fine. Now I am going to do some modification. Okay, I am going to do some modification to the Daniell cell circuit. Okay, so assume that I am going to find the reduction potential for zinc. Okay, assume that I'm going to find the reduction potential for zinc. So what I'm going to do is, okay, actually instead of speaking like this, I can tell you this. There is something called as She. Okay, there is something called as She, and the full form is very simple. It's called standard hydrogen electrode. Okay, that's the full form, right? So this standard hydrogen electrode is used for finding out the individual elements' reduction potentials. right? I told you generally we'll not be able to measure it, right? But with the help of the sheet, right, I will be able to measure the individual reduction potentials of all the elements possible. Okay, now how this standard hydrogen electrode looks, this is how it will look, right? I am going to have an electrolyte solution. In this case, I'm going to have H2O plus H2SO4, but H2SO4 is only like 2 to 3 drops, right? Majority water, but say 2 to 3 drops of H2SO4 just to increase the conductivity. I know water is a very bad conductor of electricity, right? So just to increase the conductivity, I am going to have some 2 to 3 drops of H2SO4, what to say, H2SO4 getting added to this, 2 to 3 drops of this. Okay, now I am going to insert an electrode, right? And this electrode is platinum rod, right? This electrode is platinum rod, and I am going to have a chamber covering it. Okay, I'm going to have a chamber covering it, and there'll be opening in the chamber, and through this I am going to give H2 gas. This is the overall conduction. This is the overall construction. Okay, again I repeat. So I have a vessel, I have a beaker. In that I have H2O and H2SO4. As I told you, H2SO4 is added just to increase the conductivity. Okay, now I am going to have obviously electrode. Electrode is immersed, and that electrode is a platinum rod. Okay, and this electrode will be under a chamber, right? And that chamber will have an opening. Okay, and through that opening there will be H2 gas getting supplied. That's it. This is the overall setup. Okay, right, fine. Now with the help of this, right, with the help of this standard hydrogen electrode, we'll try to understand how are we going to find the individual production potentials. Okay, now first thing is, when you are going to use standard hydrogen electrode, right, when you're going to use standard hydrogen electrode, first you have to understand whether to use it as a cathode or to whether to use as a anode, right? So we are talking about zinc and hydrogen basically, right? Zinc and hydrogen is what we're speaking about. Now tell me, from whatever the previous knowledge which we studied till now, from just now, tell me which has to be used as cathode, which has to be used as anode. Think about it and tell me. I have zinc and hydrogen. Which should be used as cathode, which should be used as anode?
H2 as anode and Zn as cathode.
Sorry?
Hydrogen as anode and zinc as cathode.
Hydrogen as anode and zinc as cathode. Okay, first things first, which is more electropositive, zinc or hydrogen?
Zinc, sir.
Yes, zinc is more electropositive. So that should be
Anode.
yes, that should be anode. Okay, so zinc is more electropositive. Now, how do you understand all this, guys? Please look at this reaction. If I have zinc reacting with HCl, I can form ZnCl2 plus H2. This is a displacement reaction. Okay, this is zinc, right? So this is a displacement reaction. Now, this reaction will happen only and only if zinc is more reactive than hydrogen. Or I would say zinc is more electropositive than hydrogen. Only then this reaction happens. So obviously zinc is more electropositive than hydrogen. So in this case, we have to use zinc as anode and the standard hydrogen electrode as the cathode. Okay, fine. So this we understood. Now we'll see how are we going to do it. Right. So let me draw the diagram again. Let me draw a circuit again. So this is your zinc sulfate, and to this I have the zinc rod, and this side I have your standard hydrogen electrode. This is platinum rod, and I have an opening, and through this H2 gas is going to come. Okay, absolutely. Now I have to connect it, right? Now I have to connect it with a voltmeter. I put a voltmeter here. Okay, I put a voltmeter and obviously the voltage. Okay, right. Now, obviously, or whatever, now if at all I have to tell you the reactions happening, at the anode, again the same stuff, the oxidation will happen. Zinc will form Zn2 plus by losing 2 electrons. Okay, now forget about what to say, H2SO4 in this thing. So eventually these two are going to give me H plus. That's all you have to understand. Okay, now this H2 and H2SO4 together, you don't have to worry about the sulfate and stuff. All that you have to understand is I'm going to have H plus, and the other thing is H2, right? How do you have Zn2 plus and zinc, right? Zn2 plus here and the zinc here, same way I'm going to have H plus and H2 are the partners. Okay, fine. So in anode, I said that oxidation will happen. Yes, oxidation is happening. And in the cathode, right, in the cathode, reduction has to happen. Right. Now think about it and tell me, you have H plus and H2, right? Converting what to what will be reduction. I have H to H plus and H2, right? Now converting what to what will be reduction. H2 to H plus or H plus to H2?
H2 to H plus, sir.
H2 to H plus, if you convert, what is happening? Am I removing electron or adding electron? Removing electron, right? So that is oxidation, right? So if I have to convert H2 to H plus, sorry, H plus to H2 for reduction, right? So in cathode, reduction has to happen. So I have H plus accepting, okay, I write 2H plus accepting 2 electron to form H2 gas. This is how you write the reaction, right? Now, please understand, the she can act as both cathode as well as anode, depending on the requirement. In this case, reduction is happening. So in this case, the 2H plus plus 2 electron reaction giving H2 is happening, right? But there might be a case where she can act as anode, and at that time, H2 will become H plus. At the time it is possible. I'll tell you how are you going to do it. Okay, fine. So the anode reaction is understood. We have oxidation, and cathode reduction is happening. Now I can even write the overall reaction. Overall reaction is zinc plus 2H plus gives Zn2 plus H2 gas is getting evolved. That is the overall reaction. Very simple. Okay, now what I'm going to do is I am going to measure the EMF, the E naught of this cell. Again, it will be E naught of the cathode minus E naught of the anode. Okay, now this value, guys, this value will be given by the voltmeter. Right, this value will be given by the voltmeter. Is it not? But the potential difference between these two will be given by this voltmeter, which is here. Right. Now, these two values are the problem. That is why we came here. Correct. Now, what you have to understand is, people, by default or by, okay, what to say, this standard hydrogen electrode, the She, I can write this actually. Right. Say this standard hydrogen electrode, right, by reference, right, it is going to be a reference point for us, right? By making it reference, what I do is the E naught of She is always 0. Okay, the E naught of the standard hydrogen electrode is always going to be 0. Remember this. Okay, now it is not absolutely 0. Right, it's not like absolutely 0, but for our convenience, IUPAC, IUPAC, right, in the International Union of Applied Chemistry, right, they said that standard hydrogen electrodes is value, the EMF of or the potential of the standard hydrogen electrode is 0. Okay, right. So what you see here is the E naught cathode. In the cathode only I have the She. Correct. In the cathode only I have She. Correct. So this value is 0. Okay, so what do you mean by that? Whatever the voltmeter reading is shown to you, that is the reduction potential for the anode, and the anode in this case is what? Zinc. Right? So like this, again I repeat what I told you now. The standard hydrogen electrode is going to act as a reference point. right? By making it reference, what we can tell is that the E naught value, the reduction potential value for standard hydrogen electrode is 0. We always assume it to be 0. Okay. Now, if that is the case, if you look at this equation, what we have here, I have E naught cell is equal to E naught cathode minus E naught anode. The cathode here in this case is your She, and that value I told is 0. So whatever the voltmeter reading which is shown to you, that will be the reduction potential for the zinc, right? So now we have found out the individual reduction potential for zinc through with the help of standard hydrogen electrode.
Sir?
Yeah.
Sir, so any electrolyte which has a H2 in it is standard electrode. Standard hydrogen electrode.
Come again, I'm sorry.
No, sir, any electrolyte which contains H2 in it, I mean H2O in it, is it
okay
called standard electrode potential, or can you say that criteria for determining the standard electrode potential, sir?
Determining the standard electrode potential.
What should be present, sir, in the electrolyte?
No. See, this She, the construction which I told you, right? This is the She, right? Obviously, the H2SO4 concentration should be 1m, right? The H2 gas should be at 1 atmospheric pressure, and this entire setup should be at 25 degrees Celsius, right? All these conditions are satisfied, and you have this setup, then the potential of this setup is 0. Okay, now you take this, you take along with all the conditions, and you connect it with whatever the element you have, say zinc and zinc sulfate, or copper and copper sulfate, or something, right? With the hell, now if you connect it, you will be able to find the individual, that is the zincs or coppers individual reduction potential, standard reduction potential you can find. Yes, did I answer your question or no?
Sir, so in the exam, will they give all the required conditions for the standard EMF? That is the temperature.
Yes. Everything they'll give. You don't have to worry about it. Yes, everything they'll give. Okay, right? So with the help of standard hydrogen electrode, we now found out the individual reduction potential for zinc, right? So now, if I have to find it for copper, right? If I have to find it for copper, there will be only one change which I do in the circuit. What will I do? Obviously, I have to include copper rod and copper sulfate, but there'll be one more major change which I'll do. What will I do?
She will become anode.
Absolutely, right? So when I talk about copper and hydrogen is more electropositive, right? So if at all you want to find it for copper will be in the cathode side, and standard hydrogen electrode She will be in the anode side, right? Because hydrogen is more electropositive than copper. Same setup, everything is same. Whatever you saw here, everything is same. Just that I'll put it ulta. She will come in the anode side, copper and copper rod will come in the cathode side. As simple as that. Again, the same thing. The voltmeter will give you a reading, and the anode's reduction potential is 0. So whatever I have in the cathode, that is your copper, I will be able to get the value. As simple as that.
Sir, I have a doubt, sir.
Yeah, tell me.
Sir, in the between zinc and She, what happened to the negative sign of E naught anode, sir?
What happened to the negative sign? Oh, you're telling that, okay. So you're telling that this anode is like the negative, what to say? The zinc is having a negative potential. Is that what you're asking? Why?
Yes, sir.
That's what I told you. Now, for this only I mentioned here that, okay, now you look at this. This is an oxidation reaction. Zinc will always undergo oxidation. But what kind of potential are we speaking about? We are speaking about reduction potential. Correct? And
yes.
That is why I told you that is going to have a negative value. And the same thing proves that, yes, it is going to have a negative value here. Because zinc is undergoing oxidation.
So the oxidation here refers to the anode.
Yes, oxidation here refers to the anode. Anode only we have the zinc, isn't it?
Yes, sir.
Right? So that will have a negative value. Obviously, the reduction potential for zinc will be a negative value for sure. And if you look at the exact value, I think it will be around 0.73, something like that, minus 0.73, something like that. That will be the value. I'm not sure. This might not be a correct value. I'm just telling you from what I remember. Okay. Right?
Okay, sir.
Fine. Cool. So now we understood the overall working of a Daniell cell, and we understood how do we measure or how do we find out the individual reduction potentials for individual elements. Okay, right? And obviously for the question, if I can follow it, if I take copper, right? If I take copper and I couple it with She, right? You will find that the copper's reduction potential value would be positive, right? Why? Because again, that's the same stuff. Maybe you will write it again, saying you write E naught cell will be equal to E naught of cathode, right? Cathode will be copper minus E naught of She, right? Now this She value will be again going to 0 because we know. So you see this will be a positive value obviously because it is shown by the voltmeter. So whatever the value will be shown by the voltmeter will be the value for copper, because now copper is undergoing reduction. So reduction will have a positive reduction potential, as simple as that. Okay, right? Fine. So this we understood. So now we'll move on. Now what I want you to know is this cell representation. How do you represent a cell? Right. Now we cannot draw the diagram every time, correct? We cannot draw, say, on cathode, anode, electrolyte, draw the vessel, all these stuff. Every time we will not be able to do it, right? So there is a shortcut representation for you to represent a cell, right? How do you represent? It's very simple. So maybe we'll take Daniell cell as example, where I use copper sulfate, zinc and zinc sulfate, right? We'll try to understand how do we represent the cell. Okay, now there'll be two kinds of slashes you use. You will use this one and you will use this one. Okay, now this talks about transformation. What is getting transformed to what, right? And this talks about the salt bridge. Okay, right. Now keep this in mind. Okay, now in Daniell cell, what is happening? Can I tell zinc is becoming Zn2 plus? That's what is happening. Correct. So I'll write zinc bar Zn2 plus. Okay, zinc bar Zn2 plus. And obviously after there is a salt bridge. You put a salt bridge, double bar. And what is happening in the cathode side? You write copper 2 plus is becoming copper. Okay, so this is what is my cell representation. Very, very simple. Right, you start with the anode, you start with the left-hand side. Left-hand side, what is happening? You see, zinc is becoming Zn2 plus. So you put it at the bar. So zinc bar Zn2 plus. After the what I have is a salt bridge, right? And then you write whatever is happening in the cathode side. Cathode, so what is happening? Copper 2 plus is becoming copper. So I write copper 2 plus bar copper. This is how you represent a cell. And also you can include the concentrations here. Zn2 plus will be 1 m concentration. Copper 2 plus will be 1 m concentration. All these things you can include. Obviously, there is no concentration for zinc and copper because they are solids, right? Only for zinc sulfate and copper sulfate solutions, we have the concentration, so that you can do. Okay, now say if at all for this particular cell, right, I have the zinc coupled with She. Okay, now how do I represent the cell? We'll see. Okay, zinc coupled with, maybe I will write it down. Okay, zinc coupled with She, how do I write? Again, so if we start with anode, okay, we start with anode, zinc becoming Zn2 plus, no issues. Maybe I have concentration of 1 m because we're talking about standard reduction potentials. Okay, now I have a salt bridge, double bar, and now what is happening? H plus is becoming H2. So I have H plus 1 m concentration becoming H2, and since it's a gas, you have to include the pressure 180. That's it, as simple as that. Okay, so zinc becoming Zn2 plus, so zinc bar Zn2 plus, salt bridge, H plus is becoming H2, so H plus bar H2. For H plus and Zn2 plus, you include the concentration. For H2, you include the, what is that? Pressure, that is 180. Okay, I hope everybody understood how do you represent the salt, not salt bridge, how do you represent the cell? This is how you represent the cell. Okay, right? Fine. Next thing, what is the time? Okay, we have 15 more minutes. 15 more minutes. When did I start? I started by 9:45. Yeah, okay, 15 more minutes. Okay, so all these stuff, guys, any doubts you have? Any doubts? We have seen so many stuff. We are learning so many new things. If there's anything you want to ask me, you can ask. Don't worry about what is the quality of the question, whether it's stupid or correct or wrong or nothing matters. If you have anything, you are welcome to ask. Is there anything you want to know? Is there any doubt you have?
Sir, is there a definition for solution pressure? When you
Oh,
first started the
definition
class,
for solution. Yeah. Solution pressure. Okay. If you want a definition, I can tell you, but it is not. It is not required for you, but still I can tell you. Solution pressure is the natural tendency of the ions to move from the electrode to the electrolyte. As simple as that.
okay.
Okay. Solution pressure is the tendency. Solution is the
Okay.
tendency of the ion to move from the electrode to the electrode.
Electrolyte. Okay.
Yeah. Right. Okay. Okay. Right. So all this we saw. Now we know how to find the individual reduction potentials of all of these, right? And how do you represent a cell? What is the working of a Daniel cell in the sense that in general a galvanic cell? What is the role of a salt bridge? All these stuff we saw today. Okay. There is just one more thing I want to tell you. Right. Say if I want to tell you, if I want to tell reduction potential of zinc. Now, how do I represent it? Right? You will represent it like this. Now, please understand, people. I know zinc will undergo oxidation, right? But since we are talking about reduction potential, we always write like this: E naught Zn2 plus bar Zn. This is how we write. Okay, E naught Zn2 plus bar Zn, because Zn2 plus bar Zn is only reduction, right? So since we are talking about reduction potential, right, this is how we write. Say now, if at all I want to give you an example, okay, say I'll take my Daniel cell. Where is my Daniel cell? Right. So I wrote here, oh, this is my Daniel cell. Ah, there's my Daniel cell. Yeah, here exactly it is. Right. This is my Daniel cell. Right. We wrote the equation here. Where is the equation? E naught cathode minus E naught anode. Where did we write? Okay, we didn't write. Okay, we'll write it here. Okay. So if at all I write E naught of cell is equal to E naught of cathode minus E naught of anode. Correct. Now, how do I represent it? This is how I represent it. E naught Cu2 plus bar Cu, obviously either it's reduction or oxidation, but the representation when it comes to the potential is always going to be reduction. Please remember this. Again, repeat the point. Whether it is oxidation or reduction, doesn't matter. You have to represent the potential, only potential with respect to reduction. Okay, so E naught Cu2 plus bar Cu minus E naught Zn2 plus bar Zn. This is exactly how we write it. Okay, so same way for if at all I want to do the coupling thing for She, and how do I write the E naught cell? Where is it? Yeah, here. Right? So here, how do you write? We'll see. Okay, so here you write E naught of the cell will be equal to E naught cathode minus E naught anode. In the cathode, I have H plus, right? So E naught H plus bar H2 minus E naught Zn2 plus bar Zn. This is exactly how we write it, right? So hope you understand. The cell representation is different, right? The cell representation, whatever is exactly happening, that you write, right? But when you come to the potential or the EMF, you always speak only in terms of reduction potentials, and reduction potential, only reduction should happen. Okay, right? Fine. So this I want to tell you. So then what else is there? Fine. Now we'll speak something. What I should have some enough time. 11:04. Okay, fine. We'll speak about it. Now that we know how to find the individual reduction potential, we can speak something about the spectrochemical series. Okay, spectrochemical series. Okay, now what do you mean by spectrochemical series? It is nothing but the arrangement of the elements, arrangement of say, okay, elements with respect to it's not basis. Right, with respect to their E naught values. Okay, so now you start with a very high, okay, you start with highly electronegative positive elements, and down, 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 down you go, and then you eventually end up with highly electronegative elements. Right? So this arrangement, starting from one element that is highly electronegative element to a highly electronegative, sorry, highly electropositive element, the arrangement till say this is one element, second element, third element, fourth element, fifth element, at last you will have the most electronegative element. And all this is not with respect to electropositivity and electronegativity, it is with respect to the E naught value. Okay, right. Now how do we do it? Maybe if I can have, maybe wait, I'll 1 second. I will actually show you in Google how it looks. Yeah, spectrochemical series. All I want is an image. Where is the image? Is it spectrochemical or electrochemical? I mean, am I doing it wrong? 1 second. Oh, yes. I'm sorry, guys, it's not spectrochemical. Spectrochemical will come under, what is that? Your coordination compounds. I'm sorry, it's electrochemical series. Okay. I hope you're able to see this. Are you able to, maybe I'll make it full screen?
So we're able to see the notes which you are writing.
Oh, you're able to see only the notes? Oh. Wait. Okay, now you're able to see?
Yes, sir.
Right. So you look at this. This is what is called as my electrochemical series. You look at this, say lithium is there, right? So lithium is having a reduction potential value of minus 3.03. Now I told you, now natural tendency of lithium is to undergo oxidation, obviously, correct? Now, not only this, you see lithium, sodium, calcium, potassium, magnesium, aluminium, zinc, iron, lead, till this, okay, look at the hydrogen, we saw it's 0, right? Standard hydrogen electrode is 0, correct? Right. So till this point, all the reduction potential values are negative. Okay, till this point, all the reduction potential values are negative. Now, what do you mean by this is all these elements, what this, see, look at the reaction here. Look at the reaction. Reaction is Li plus electron giving Li, but this is not a spontaneous reaction. This is not a spontaneous reaction, correct? And that is the reason why you have a negative value of reduction potential, because natural tendency of these elements are to undergo oxidation, correct? But what we are taking is reduction potential, and that's the reason why we have so much of negative values happening, right? 1 second. Right, now after hydrogen, you see standard hydrogen electrode is 0, that I already mentioned. Now you look at all the other elements after that, right? All the other elements are having actually a positive symbol, I mean positive value of reduction potential. Now what do you mean by this, right? What do you mean by this is that these elements have the natural tendency to undergo reduction, and above hydrogen, whatever the elements you have, they're having negative value of reduction potential. That means they have natural tendency to undergo oxidation. Okay, so whenever you see a negative value of reduction potential, that means that particular element has natural spontaneous tendency to undergo oxidation. And whenever you see a positive value, that means that particular element can easily undergo reduction. That's what you have to understand. Okay, now this will all be very clear if I bring in thermodynamics here. Okay, now you don't have to remember like, okay, a negative value means it is undergoing oxidation, positive value means undergoing reduction. No, we are not going to speak like this. If I bring in thermodynamics, right, you are absolutely going to understand what exactly is happening here. Okay, so let me go for that. I'm just going to give you one equation. Okay, again, it's not spectrochemical series, guys, it is electrochemical series. Yeah, please go.
So it starts from the most highly electropositive to highly electronegative, sir.
Yes. Oh, but okay. What you're asking
And
is,
if
but
it's
there are
electronegative.
no electronegative elements. Maybe if I can show you, like in that table it is not there. Maybe in some other table it will be there. Maybe let me show you one second. Anything else I'm seeing? Yeah, I think this will have. Or this thing is not clear. Maybe I'll view the image. I'm seeing only metals. Maybe it's not this. Okay, at least this has some negative ions. I think this we can see. Okay, now you look at this. I put this, I will little. Okay, now you see, now in this case, they started with, in this case, they started with the opposite. They say they started with highly electronegative element, that is F2, and they ended up with lithium. Okay, so F2 will have very high positive value, and it just keeps on reducing. You have this is not standard hydrogen electrode, people. The second one, what you see here is not standard hydrogen electrode. You see it's H2O2, hydrogen peroxide. Okay, now that comes after the chlorine comes, oxygen comes, bromine comes, and eventually you will see that for standard hydrogen electrode it is 0, right? And eventually you will see that all the other metals which have natural tendency to undergo oxidation will have negative values. Okay, is it okay, Rohan? Is it fine?
Yes, sir. Yes, sir.
Okay, right. Okay, now I'm going to give you just only one equation, and with that equation, everything is going to come very clear to you. Okay, right. So the equation is, I told you that I'm going to bring in thermodynamics, and I'm going to bring in thermodynamics, and I'm going to connect it with this reduction potential values. Okay, the simple equation is this: delta G naught is equal to minus NF E naught. As simple as that. Okay, this equation is very, 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 very important. Okay, delta G naught is equal to minus NF E naught. Okay, I'll tell you, E naught is very simple. E naught is my reduction potential. Right, now this N is the number of electrons involved. Right, for example, you take zinc. Right, zinc is losing how many electrons? 2 electrons, right? So the N value will be 2 for zinc. Again, for copper, it will be 2. For hydrogen, again, it will be 2. Because you have 2 H plus, right? 2 H plus becoming H plus, accepting 2 electron to form H2. So again, it is 2. Okay, so what you have to understand is N is nothing but number of electrons involved in that particular reduction or oxidation process, whatever it is. Okay, now this F is a quantity which I'm going to define. F, 1F is charge of 1 mole of electrons. Very simple, right? 1 Faraday, F is Faraday. Okay, right? It's a constant value, right? How do you have, say, a Boltzmann constant, that universal gas constant, so on and so forth? F is a constant. Okay, 1F is nothing but charge of 1 mole of electrons. Okay, now I think I'll be able to easily calculate this value. Is it not? Now I know charge of 1 electron is how much? Tell me. What is charge of 1 electron in coulombs?
1.6 into 10 to the power minus 19.
Yes, minus 1.6 into 10 to the power minus 19 coulombs. But we don't have to include this negative sign because it doesn't matter. Anyways, now in 1 mole of electrons, how many electrons will be there?
6.022 into 10 to the power 23 into 1.6. That is minus 1.6 into 10 to the power.
Understood. Understood. Yes, yes, yes. So in 1 mole of electron, I will have this many numbers of electron. And each electron is having a charge of 1.6 into 10 to the minus 19 coulomb. Correct. So now how do you define 1 Faraday as charge of 1 mole of electron? So total 1 mole of electron, totally how much charge they have, that is what is 1 Faraday. So what you have to do basically is you have to multiply this value and this value. right? This is charge of one electron, and this is the number of electrons. So total will be the multiplication of this. So 6.023 into 10 to the power 23 into 1.6 into 10 to the power minus 19. So approximately you can have 1F value as 96,500 coulomb per mole. The unit is very important. Okay, 1F is 9 approximately. Again, the exact value will be 96,487 point something something. It will be like that. Okay, but you can always use this value directly. Okay, 96,500 coulomb per mole is what is my what is that? 1F, the Faraday value constant. That's the value of the constant. Okay, now do I have time to explain you how? Yeah, no guys, right? So we'll stop here. Okay, now this equation is going to help me easily find out why do I have a negative sign for certain elements, why do I have a positive sign for certain positive sign of electrode potential, that is reduction potential, why certain elements will have negative value of reduction potential, why certain elements will have positive value of reduction potential. All these questions will be answered by this equation. Okay, and we'll try to consider the equation in the next class. Okay, so I have, like, we have seen a lot of stuff today, right? Lot of new things we learned today. So hope you spend some time. You can read your book if you want, right? You can read your NCERT textbook and see whatever we are learning here. Okay, if there's no doubt, we can wind up the class.
I have
Is there any question? Yeah, please go on. Go on.
So what is this equation used for, sir, to find out what exactly?
Oh, like this equation is basically connecting my delta G, that is thermodynamics, with electrochemistry. Okay, this is the reduction potential value, and this is my Gibbs free energy, which we already know, right? So we spoke about spontaneous chemical reactions and galvanic cells and all that, right? So basically, to check whether a particular cell can give me a potential or not will be decided by the value of delta G. So if the overall delta G of the cell is negative, then only I can tell that that cell can be formed, so on and so forth. A lot of information you will be getting, right? We will spend so much time on this equation in the next class. You will get more insights about it. Don't worry. Okay?
Yes, sir. Understood.
Yeah. Any other questions, guys? Okay, I suppose there are no questions. Thank you so much, people. Thank you so much for joining. It was a wonderful class. I hope you learned a lot. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, yeah. Thank you.